My name is Divij Gupta, and this is a video abstract for the paper Generalized Spectral Statistics in the Kicked Ising model by Swingle and myself. Random matrix universality is a central pillar in the field of quantum chaos. In the context of periodic systems, it suggests that the spectrum of the Floquet operator must resemble the statistics of a random matrix ensemble. The Kicked Ising model is an exactly solvable model exhibiting quantum chaotic dynamics and provides an interesting testing ground for this idea. The model is described by a chain of L interacting qubits with a transverse field applied along the chain, to which we apply a periodic kick. The chain can have either open or periodic boundary conditions. The case of periodic boundary conditions has been studied previously, with the central object of study being the trace of the Floquet operator, the return amplitude. The spectral form factor is then the second order moment of this quantity after disorder averaging over the transverse field. Higher order moments can also be studied, and the particular dependence of the higher order moments on the SFF can be used to determine the statistics. For periodic boundary conditions and in the thermodynamic limit, the SFF has been explicitly computed and the higher order moments shown to align with the statistics of a real Gaussian. In this paper, we investigate the role of boundary conditions on these statistics. We start by reviewing the periodic result and providing an alternate derivation of the higher order moments. This is done by extending the transfer matrix approach of previous analyses, where the SFF is shown to be equal to the trace of a temporal transfer matrix. We compute the higher order moments by defining an analogous higher order transfer matrix and constructing its eigenvectors by pairing eigenvectors of the second order matrix. The number of these pairings suggest higher order moments equal to those of a real Gaussian, reproducing the previous results. We also find that for open boundary conditions, these statistics are no longer obeyed. Instead, numerical analyses suggest that the return amplitude obeys complex Gaussian statistics, making the appropriate random matrix ensemble the circular orthogonal ensemble. We also propose an analytic computation of this result using the transfer matrix methodology, where the trace of the transfer matrix is replaced with a matrix element determined by appropriately defined boundary vectors. These boundary condition dependent statistics can also be studied by computations of the Low-Schmidt SFF. This is a generalization of the SFF where the forward and backward time evolution operators are not equal. For the Kicked Ising model, we take the forward and backward Hamiltonians to have transverse fields that are drawn from distributions that are no longer identical, but correlated. We study the system in the perturbative regime where the correlation is nearly perfect, with the perturbation parameter delta. We use the transfer matrix methodology to find that the quantity has an exponential decay following the SFF ramp, which is verified numerically. We also compute a similarly defined deformation of the fourth moment of the return amplitude and show that the behavior is dependent on the boundary conditions. In the discussion, we discuss the results of an analysis for parameters deviating from the self-dual points, which are parameter values such that the transfer matrix is unitary. We also discuss directions for future work, including a complete analysis of open boundary conditions, extending the result to even times, and studying corrections to Gaussianity. Thank you.